So chemistry is quantitative. We measure the properties of matter, and we do calculations with those measurements. When you do calculations in chemistry, it is very important to make sure you deal with the units in the calculation appropriately. Here are a few things to remember regarding units. First, always write every measurement with its associated unit. The unit tells us the property being measured and the scale used to measure it. Second, always include the units in your calculations. All the operations you do with numbers, you can do with units. It's easiest just to treat them like you would variables in algebra. So if you know in algebra that x times x equals x squared, then you also know that 1 centimeter times 1 centimeter equals 1 centimeter squared. You also know that x plus x would equal 2x in algebra. So 1 centimeter plus 1 centimeter equals 2 centimeters. You can also do subtraction in the same way. 3x minus x gives us 2x. And 3 centimeters minus 1 centimeter equals 2 centimeters. And finally, we can do division. In algebra, x divided by x would cancel each other out, leaving us with just 1. In the same way, when we divide units that are the same, the units can cancel each other out, leaving us with a unitless number. So 1 centimeter divided by 1 centimeter would equal just 1. This last relationship is particularly important for a major set of calculations that we do in chemistry. We often have to convert from mass to amount of atoms, or volume to mass, or some other type of conversion in chemistry. In order to do this, we take advantage of a problem-solving method called dimensional analysis. In this method, the units are our guide to figuring out what to divide and what to multiply. Let's review how we treat units in calculations of volume and density. Say we want to calculate the volume of a penny. A penny is a regular geometric cylinder, so we can use the formula for calculating the volume of a cylinder. This is the constant pi times the diameter of the penny squared times the height or thickness of the penny divided by 4. We measure the dimensions. The diameter is 1.9 centimeters and the height or thickness is 0.16 centimeters. We can plug these values into our formula. Remember that if we square a measurement, like 1.9 centimeters squared, we have to square both the number and the unit. So the term in parentheses becomes 3.61 centimeters squared. And when we multiply two measurements together, the units also multiply together. So 3.61 centimeters squared times 0.16 centimeters becomes 0.5776 centimeters cubed. Finally, we can multiply by the constant pi, divide by the number 4. Both of these values are unitless, so they don't change our centimeter cubed unit at all. And what we get is 0.45 centimeters cubed. If we've also measured the mass of the penny, we can calculate density. We can plug our mass of 2.5 grams and our volume of 0.45 centimeters cubed into our density formula and divide. Now notice that the units of grams and centimeters cubed don't cancel each other out. They have to be the same unit to cancel each other out. It's the same as dividing the variable x by the variable y in algebra. They're not the same variable. They will not cancel each other out. As a result, the final units of density have to be grams per centimeter cubed. Both of the previous problems involved formulas that we could plug our numbers into and solve. More often than not in chemistry, though, our calculations don't have a set formula to follow. Instead, we just need to convert from one unit or property to another. And this is when we have to use dimensional analysis. Here's a good example of that conversion. The average atom has a diameter of 0.3 nanometers. What is this in meters? Well, I don't have a set formula I can plug into. I do have a set of general problem-solving steps for dimensional analysis or unit conversion problems. We always start by looking at a problem and determining our given information. In particular, we're looking for the amount and unit that we're going to use as the starting point for a calculation. In this case, we're given that an atom has a diameter of 0.3 nanometers. Next, we look at the problem and figure out what unit we need to have in the final answer. In this case, we want to find the equivalent measurement in units of meters. Next, we need to know what the relationship is between meters and nanometers. This is known as an equivalence statement. It's a constant relationship that defines how many of one unit equals another unit. Meters and nanometers are both metric prefixes, so I can look back at my metric prefix relationships and discover that 1 nanometer equals 10 to the negative 9th meters. I'm going to use this equivalence statement to convert from what I've been given to what I want to find. And I do this by setting it up as a conversion factor or fraction. I always set up the calculation starting with my given measurement and its unit. In this case, we start with 0.3 nanometers. I'm then going to multiply it by a conversion factor or fraction made up of the 2 halves of the equivalence statement. Since I want to get rid of my starting units of nanometers, I put the half of the equivalence statement with nanometers in the denominator of the fraction. This is because when we multiply this through, you always divide by the denominator of the fraction. And as you remember, when you divide units that are the same, they cancel each other out. So nanometers will cancel out with nanometers. Now, if I had a starting unit of just plain meters, I would have put the other half of the equivalence statement in the denominator of that fraction. I don't. I have nanometers, so we're going to keep 1 nanometer in the denominator. On the numerator, we put whatever is on the other side of our equivalence statement. And this will be the unit that we convert into. Last but not least, we multiply all terms across the top and divide by each denominator term. We do this for both our numbers and our units. In terms of the units, nanometers divided by nanometers cancels each other out, and then we multiply by meters, which is going to give us a final unit of meters. 0.3 times 10 to the negative 9th divided by 1 is actually the same as 3 times 10 to the negative 10th. So our final answer is 3 times 10 to the negative 10th meters. That's the average diameter of an atom in units of meters. Knowing or being able to find the appropriate equivalence statement is the key to this type of problem solving. For conversions within the metric system, the equivalence is determined by the prefix relationship. Here are sample equivalence statements for each of the common prefixes that you'll encounter. You can substitute any base unit into these equivalence statements. For example, we could also say that 1 kilogram is equal to 10 to the third or 1,000 grams. The numbers and prefixes stay the same as in the sample equivalence statements given. You can also find equivalence statements for non-metric units of measurement. Your textbook contains many of these equivalence statements in Chapter 1. You can also find these by doing a quick search for equivalences or conversion factors online. Let's try another problem. In this case, we're given the distance between the Haverhill and Lawrence campus in miles. We're asked to find the equivalent distance in kilometers. We look up our conversion factors and find that 1 mile equals 1,609.3 meters. This is not quite the final unit we want, but we also know a second relationship that can relate meters to kilometers. Based on our metric prefixes, we know that 1 kilometer equals 1,000 or 10 to the third meters. We can use both of these conversion factors in our problem. We'll start with our given number and unit of 12 miles, and we'll multiply it by the conversion factor that cancels out our given unit. So that's the first equivalence statement. That's the one that contains miles. So that the mile unit cancels out, we put the half that contains miles in the denominator. The other half has to go in the numerator. Miles cancels out, and we'll be left with units of meters. We still need to convert this into kilometers, but we can easily do this using our second equivalence statement. We just set up another fraction or conversion factor. So now we want to cancel out our meters. So we set up the half of the second equivalence statement that contains meters in the denominator of the second conversion factor, and the other half, the kilometers, has to go on top. Now all of our units cancel out with the exception of kilometers. Miles divided by the denominator in our first conversion factor cancels out. That leaves us with meters, but then we multiply by the second conversion factor, and the denominator of meters cancels out, leaving us with our final unit of kilometers. We also multiply and divide through by the numbers. 12 times 1,609.3 divided by 1 times 1 divided by 10 to the third, or 1,000, gives us 19 kilometers. Almost all unit conversions can be done using the dimensional analysis method, with one exception: temperature units. This is because the temperature scales are offset. All temperature scales are based on the freezing and boiling points of water. In the Celsius scale, the freezing point of water is set at 0 degrees Celsius, and the boiling point is exactly 100 degrees higher than that. The Kelvin scale is also set, so there are exactly 100 degrees between boiling and freezing. But the freezing point in the Kelvin scale starts at 273.15 Kelvin instead of 0. This means that we can convert from degrees Celsius to Kelvin simply by adding 273.15. The conversion between Celsius and Fahrenheit is a little more complex. The freezing point in the Fahrenheit scale is 32 degrees. But between the freezing point and the boiling point, there are actually 180 degrees Fahrenheit. This means that there are 180 degrees for every 100 degrees Celsius, or if we reduce that, 9 degrees Fahrenheit for every 5 degrees Celsius. We need to account for both this difference in size of the degree as well as the 32-degree offset for the freezing point of water. This gives us the conversion equation for degrees Fahrenheit of 9/5 times degrees Celsius plus 32. Let's look at these formulas in practice. Normal body temperature is 37 degrees Celsius. What is this in Kelvin and degrees Fahrenheit? The formula for the conversion between Kelvin and degrees Celsius, again, is here. So all we need to do is add 273.15 to our 37 degrees Celsius, and we get our Kelvin temperature, 310.2 degrees Kelvin. For the conversion to Fahrenheit, again, we substitute in our 37 degrees, we multiply that by 9 and divide by 5, and then add 32 to give us 98.6 degrees Fahrenheit. Converting from degrees Fahrenheit to degrees Celsius can be a little bit trickier, but remember that you just need to rearrange algebraically this equation to solve for degrees Celsius. So we substitute in our 50 for the degrees Fahrenheit in the formula, and we want to get degrees Celsius by itself. The first step is to get rid of the added on term, the plus 32. Algebraically, we can eliminate that term by subtracting 32 from both sides. So it cancels out on the right-hand side, and we end up with 50 minus 32, or 18, on the left-hand side. To get rid of the 9/5 term, since this is multiplied, we have to divide by it on both sides. Now, division by a fraction is the same as multiplying by the reciprocal of that fraction. What that looks like is multiplying by 5/9. On the right-hand side, that cancels out with 9/5. And on the left-hand side, we end up with 18 times 5 divided by 9, or 10 degrees Celsius. So in summary, units multiply, divide, add, and subtract in calculations, just like variables in algebra. You can use equivalent statements as conversion factors in dimensional analysis to convert from one unit into another. Temperature conversions, however, require formulas, not dimensional analysis.